Hello everybody, welcome to this video. Here we have a series of previous year's UGC NET questions, and right now we are focusing on linear algebra, and this particular problem was there in December 2014 and it was of 3 marks. So the question is, which of the following is not a diagonalizable matrix over R? So you are given 4 matrices and you are asked which one of the following matrix is not diagonalizable. Right, now you should remember some theorems. So you see we have this theorem that if all the eigenvalues of a matrix are distinct, then it implies that matrix is diagonalizable. But this is only one-way result, right? Then we have a two-way result which says that T is diagonalizable, T n cross n matrix is diagonalizable if and only if it has n eigenvalues, and for each eigenvalue algebraic multiplicity is equal to geometric multiplicity. Right, so these are the two results we have. So let us look at the first one. Is simple to imply, but this is one way, and second one is little bit hard to apply, but this is two way if and only because of this. Now here if you look at these matrices, all the three matrices, they are upper triangular matrices. So note down, all the three matrices are upper triangular matrices. Therefore its eigenvalues are just the diagonal elements. This you know, right? Therefore if you call it as A1, call it as A2, call it as A3, call it as A4, so eigenvalues of A1 are 1 2 1, of A2 are 1 2 3, if of A3 are A3 your matrix is 1 1 2, and for A4 are 1 2 3. 1 2 3, 1 2 3. Now from the first result, see here and here, these are distinct eigenvalues. So distinct eigenvalues, therefore diagonalizable. Here also distinct eigenvalues, therefore diagonalizable. So option B and D, they are gone. B is not the option because we are looking for a non-diagonalizable matrix, and D, these two options are gone. Now we are left with the first and third option. Let us look at first option, A1, that is your matrix 1 1 0 0 2 0 0 0 1. Here eigenvalues are 1 and 2, right? So 1 has algebraic multiplicity 2 because 1 is repeated 2 times, and 2 has algebraic multiplicity 1, and we know that this will be equal to geometric multiplicity. So if any multiplicity is 1, that is same, because we know that at least geometric multiplicity is 1, because that is for sure corresponding to that eigenvector value. You will get an eigenvector, and that eigenvector will span whole space with dimension 1. So whenever the AM is 1, you don't need to check for GM will also be 1, right? But here AM is 2, then you need to check the geometric multiplicity of 1. For GM of 2, geometric multiplicity of 2, what you need to know, for 1, geometric multiplicity of eigenvalue 1 is 2, and we have to compute its geometric multiplicity. So you need to solve A minus lambda I into the vector is equal to 0. Here lambda is 1, so you need to solve A minus I, that will be 0 1 0 0 1 0 0 0 0 into x y z is equal to 0 0 0. So here you see what you get. You get x is equal to first equation will give you y is equal to 0. Second equation will give you y is equal to 0. Therefore your eigen space corresponding to eigenvalue 1 looks like, how does it look like? It looks like x, y, z is equal to, x is as such, y is 0, z is as such. So this is x into 1, 0, 0 plus z into 0, 0, 1, where x and z are real. So it has, therefore its dimension is 2, because it is spanned by these two linearly independent vectors. So its dimension is 2. Therefore am is equal to gm for lambda is equal to 1. Already am is equal to gm for lambda is equal to 2. So you get it. Whenever the algebraic multiplicity for any eigenvalue is 1, you don't need to check its geometric multiplicity. That will be for sure 1. Right. So here we get that this matrix is also diagonalizable by this second theorem. Right. So A1 is diagonalizable. A1 is diagonalizable by second theorem, by second result. Right. So this option is also gone. Right. So some of you may directly put this as correct option, but I will recommend you always C. Now let us look at third option, AC. A3. Your A3 is 1, 1, 0, 0, 1, 0, 0, 0, 2. Its roots, eigenvalues are 1, 1, 2. Therefore, algebraic multiplicity of lambda equal to 1 is 2. This is repeated 2 times. And algebraic multiplicity of lambda is equal to 2 is 1, because it is repeated 1 times. So here this is equal to geometric multiplicity. We don't have to worry. We have to check for lambda is equal to 1. So let us see. For that we need to check a minus lambda is 1, I, x, y, z is equal to 0, 0, 0. So what you'll get? You'll get 0, 1, 0, 0, 0, 0, 0, 0, 1, x, y, z is equal to 0, 0, 0. The first equation gives you y is equal to 0 and the last equation gives you z is equal to 0. So eigenspace of lambda is equal to 1. Eigenspace of lambda is equal to 1 looks like, you see how will it look like? X, y, z, which will be x is x, y is 0, z is 0. So this is x into 1, 0, 0, where x is any real number. Right. So it is spanned by this single vector. Therefore dimension is 1. Therefore geometric multiplicity of lambda is equal to 1 is 1. Right. Which is not equal to its algebraic multiplicity 2. Therefore it is not diagonalizable. Fine. So this is how you see. So your option C is the correct option, that this is not diagonalizable. So answer to this problem is C. Right. So here you see, you need to know these two results. First result this one and second result this one in order to solve this problem. Please keep trying to perform in a better way in the exam. Thank you for watching this video. Please subscribe to this YouTube channel, and in the comment section please write your comments, your suggestions, and your anything which you want to discuss. Thank you.